Hi, in this video we're going to be looking at messaging and synchronizing in the RTX RTOS. Intertask communication are very important in a OS design, okay? Basically because as we have seen, multiple threads are always running and you can have a lot of context switch happening all the time. Okay, so there must be a very reliable and effective way for tasks to communicate with each other. Okay, in terms of this aspect, what we have seen so far is we have seen the use of mutex and semaphores. Okay, mutex generally has been used, okay, in the area of protecting a critical section of the code, okay, where there is access to a shared variable or shared resource between multiple tasks. Semaphores, as we have seen, we can use it in a few different contexts. Okay, one is uh, if you declare a semaphore with a value of 1, okay, then it becomes a binary semaphore. Okay, and a binary semaphore is also equivalent or in a sense can be used in the same way as how we use a mutex. That is one. Another aspect of semaphore we have seen is synchronization. Okay, if you recall in the lab as well in the last lecture, we saw that one task, the interrupt task, will release a semaphore and the other tasks are waiting for a semaphore. Okay, so that was synchronization aspect of using semaphores. Okay, and today what we are going to be looking at is three other aspects of it, or mechanisms of the RTX that allows us to fulfill synchronization. Okay, and of course one more which also provides data communication. The first two we're going to look at is flags and events, and the last one is basically what we call mailbox or message queues. Okay, mailbox was the generally older terminology. Now we are calling it as message queues. Okay, so let's look at them one by one and understand how they can be used in the RTX to fulfill the objectives of synchronization, okay, and as well as data communication. The first one are we're going to focus on our thread flags. Okay, so thread flags are not created, they actually exist automatically within each thread. Okay, so the moment you create a thread, there is already 31 thread flags associated with each of the threads. Okay, from 0 all the way to 30 over here. Okay, so total of 31 thread flags. And what we have is we have the ability for one thread to set the thread flags in another thread. Okay, and how do we do it? We address it using its thread ID. Okay, now what is a thread ID? A thread ID is actually the return value that we get, okay, when we create a new thread by calling os thread new. Okay, in the past few lab exercises we haven't actually looked at the return value, but now we're going to be looking at this. Okay, and what we need to do is we first need to declare a global thread ID variable, something like this. Okay, os thread id t red led id, and when we call os thread new, the id of this thread that we create will be stored inside this variable called red led id. Okay, and we will use this thread id for the implementation of thread flags. Okay, so let's see the thread flags associated kernel calls. So the two main calls are os thread flag set, okay, where I specify which thread I'm referring to and which are the flags I want to set. Okay, the other one is os thread flags wait. So this is the thread that is waiting for certain flags to be set. So I specify the flags over here, I specify the options and the timeout. Okay, so in terms of options, there are three options here. Okay, first one is wait for any of the flags. So if I'm waiting for a couple of flags, as long as any of the flags are set, then I can proceed. The other one is which is wait all, is to say that I want to wait for all the flags to be set, then I will proceed. And in both these options, the moment I proceed, I will actually clear the flags. Okay, but there's also an option to say that I do not want to uh, clear the flags. Okay, so that is this option over here. So these are things that you can try out, okay, in the lab exercises to have a better understanding of how they are actually working, okay, in a multi-threaded environment. So let's look at an example, okay, on how we can use flags. Okay, so here we have two threads, okay, LED on and LED off. Okay, and what we are doing is we have the thread ID of LED off, which is this. Okay, so when I called OS thread new for this particular thread, this was the thread ID was returned and stored inside this variable TID LED off. Okay, and as you can see, what is happening here is when LED on the thread 1 runs, it switches on the LED. Okay, so this is what is happening. So initially it's off, then it switches on the LED signal, and then what I do is I set the flag for the LED off thread. Okay, and what is the value? I set it to a value where the bit 0 is 1. Okay, so you have to understand that the thread flags are all accessed as individual bit flags. Okay, so this one refers to bit 0, so bit 0 1 2 3 all the way to bit 30. So this bit 0 is now set to 1. Okay, so that is what is happening over here, and after that I do a delay of 2 seconds. Okay, so once I go OS delay 2 seconds, I am going to a block state, and I will allow so effectively thread 2 will also get a chance to run. And when thread 2 runs, you can see that the first thing it does is it actually waits for the thread flags wait. Okay, and this is referring to the flag that I'm waiting for. So I am also waiting for bit 0 flag to be set. Okay, so 30 3 2 1 0, so bit 0 here, so I want this flag, okay, to be set. In this case, in this example, I've used this option called OS flags wait any. Okay, that means, okay, uh, in this case it makes no difference because I'm only looking for a particular flag to be set 1. Okay, but in the next example we will look at where there's a difference between wait any and wait all. Okay, and the last option is wait forever. That means as long as this flag, okay, has not been set by any other thread, I will be waiting here in a block state. Okay, and once that flag has been set, I will come out of the block state, go to a ready state. Okay, and in the ready state, what do? I will delay for 500 milliseconds, which is here, and then I will call LED off. Okay, which is this. So I'll go down here. Okay, so I'll be off, and when the 2-second timeout finishes, I'll come back in to the beginning of the loop and I will repeat the whole process again. Okay, so that is basically what these two threads are running or fulfilling, okay, in terms of controlling this LED on or off signal. Now at first glance, when you look at this, you can say that it's a bit similar to what you did for semaphores. You know, one task can post a semaphore, okay, and the other task can acquire a semaphore, okay, and be blocked until the semaphore is available. So in that sense, yes, you know, you can say that this could have also been achieved using semaphores. But where does the thread flags advantage come in is you have the ability to set multiple flags and wait also for multiple flags. Okay, so let's look at the next example. So in this example, we have 3 threads, thread 1, thread 2, and thread 3. And what you are seeing here is, regardless of whichever thread runs first, doesn't matter. So imagine that, let's say thread 3 runs first. Okay, so because priority is not clearly shown here. Okay, but just assume that, let's say thread 3 runs first. The first thing that I do is I wait. Okay, and I wait for threads bits 0 and 1 to be set. Okay, so the 3 here is referring to hexadecimal 3. Okay, so if I look at the binary bits 30 all the way to 3210, okay, so this is the 31 thread flag. So 0x0003 refers to this bit to be set and this bit to be set. Okay, so this is the 3, correct? So what I want is I want the thread flag 0 and thread flags 1 to be set. Okay, and as you can see here, the option says that I want to wait for all the flags to be set. OS flags wait all. So in this case, I will only proceed when both bit 0 flag and bit 1 flag are set. Okay, and I'm going to wait forever. Correct. So until then, I will be blocked and waiting. So eventually, when thread 1 runs, I will set the bit 1. sorry, bit 0 flag. And when thread 2 gets a chance to run, I will set the bit 1 flag. Okay, so this is if I look at the bits 3210, this is this bit over here, and this is 10, this is this bit over here, correct? Okay, so what is going to happen is thread 1 must set the bit 0 flag, thread 2 must set the bit 1 flag, and thread 3 is waiting for both these flags to be set. Okay, and this is one of the advantages of using thread flags, okay, where you, instead of having multiple semaphores, okay, to handle communication between uh, different threads or waiting for different type of synchronization, you can do something like this, where one thread is waiting for a few other threads to have completed or some task and sort of signal this current thread that is waiting. Okay, so thread 3 is waiting, okay, for these flags to be set, and then it's going to carry on. Okay, so that is one way of synchronizing thread 3 to thread 1 and thread 2. Okay, so you can say that when thread 1 and thread 2 both have completed some level of activity, they will set these flags. Okay, and when these flags are set, then thread 3 can carry on. Okay, so of course, as you can see here, the thread ID is thread ID 3, which refers to the thread ID that you would have gotten back when you first created thread 3 using the OS thread new kernel call. Okay, so that is an example of using flags. Now, the next communication uh, approach we're going to look at is what we call events. Okay, and events are actually very similar to flags. Okay, they're very similar to flags. Okay, except that they are not tied to any particular task. Okay, what we need to do is we need to create a new events flag object, and similar to thread flags, we have 31 event flags. Okay, so the first thing is we want to call event flags new to create a new event flags. Okay, and after that we can use it by either setting it or waiting for it. So the options wise, you can see they're very similar. Wait for any, wait for all, and no clear. Timeout is the same as before. And flags are, which are the flags that you are waiting for to be set. Okay, the only additional parameter here is the ID, and this ID is basically what you send, okay, or what you get back when you create the event flags new. Okay, so now let's look at an example. So over here what we have is we have created a event flags ID called LED flag, and we're going to call the OS event flags new, okay, in the main app. Okay, so this is the main task or the first task that runs. Okay, and we're going to create this event flags new, and then we have two other tasks here, LED on and LED off. And what you see is happening is, okay, let's assume the LED on runs first. So it will switch on the LED. Okay, so it will switch on the LED over here, and then it will set the LED flag. Okay, so what is the difference between this and the thread flags just now? In the thread flags, this was specific to a particular thread. So we were explicitly setting the flags for a particular thread. In event flags, we are setting it for this new event flags variable that we have created. Okay, so the difference is this LED flag, okay, can be accessed by any thread. Okay, it's not tied to a particular thread. That's the main difference. Okay, and now what we are doing is we are setting again the bit 0. So this refers to bit 0. Okay, and then we are having a delay, and the LED off thread, when it runs, it is calling the OS event flags wait, okay, for the same LED flag, okay, again for bit 0, and in this case wait any and wait forever. So as long as once that flag has been set, I'll come out of this block state, then I'll delay for 500 milliseconds, which is this, okay, and then I'll call LED off. Okay, and then when the 2 seconds delay expires, I'll go back in and repeat the whole process. Okay, so you can see effectively the event flags and thread flags are very similar. Okay, only difference is thread flags you are specifically sending or setting the flags for a particular thread, In event flags, you are setting it to a event flags variable which can be accessed by any thread. Okay, so that is the main difference. Okay, so the next important thing we're going to look at is message queues. Okay, message queues are very important, okay, because they allow you to send data, okay, or communicate between different threads by sending messages in this message queue. Okay, and you can control, okay, you can send, receive, or wait for messages, okay, and that allows a very efficient mechanism to do two things in parallel. One is to synchronize, okay, when a thread should run or should wait, and while synchronizing, you're also performing data transfer at the same time. Okay, so message queues are a very important aspect of multi-threaded programming. Okay, how do we use message queues? We first create a message queue, okay, by calling OS message queue new, okay, by putting in the count as well as the size, okay, of the message queue, and subsequently any task can put a message by calling OS message queue put, and any task can wait for a message by calling OS message queue get. Okay, so let's look at this in a more practical way. Okay, how can I use these message queues for my project or for any other application? Okay, so the first thing you want to do is you want to declare a message data structure. Okay, for our mini project, okay, that you're working on, I would say generally a single 8-bit variable should be enough, okay, to hold the information that you need. Okay, but I'm just intentionally showing you, okay, data structure with two 8-bit variables, just to give you the idea that I can extend this to make it even much larger, so the message that I send can be very comprehensive to hold a lot of information. Okay, so it can be a very simple 1 byte data, or it can be a multi-byte array with a lot of information. Okay, so in this example, we have a structure where the first character is a, or 8-bit data is a command, the second 8-bit data is the data itself. Okay, and then what we do is we create a message queue ID for the three different LEDs that we are going to control: red, green, and blue. Okay, and then what we're going to do is we're going to create three message queues. Okay, and these three message queues are for the three different LED threads. Okay, and as you can see, there are two parameters or three parameters. The first one is message count. How big is the message queue going to be? In this case, I've just defined it as 1. Okay, so I only going to handle one message at a time. I don't want to have multiple messages in my buffer. Again, this is a design choice. It's up to you, okay, whether you want more or less. Then how big is the data? That is the size of my data packet, okay, which is what we created just now. Okay, and these are the attributes. For now we have put as null. Okay, so if I look back here, you can see that the this last um, parameter, which is attributes, we just keep it as null. Okay, and that works for most of our cases. Okay, once we have created the OS message queue new, we are now ready to use the message queue. Okay, and what I have done is I've just created this simple representation of the data where the command and data is representing some information. Okay, and since I have separate message queues for different LEDs, okay, I just going to fix it as 1 for red and 1 for blink. Okay, this is again just to give you the idea of how it works. In the lab, you are going to actually extend this, okay, where you're going to modify this structure a bit, okay, to hold more information such as how fast you want the LED to blink. Okay, so that is something you're going to be exploring in the lab. Okay, so what I've done, which is also what you're going to do in the lab, is I've created a new control thread. Okay, so instead of having a push button or some button press from the app coming through, okay, we are just going to simplify it and have a control thread. Okay, and what does this control thread do? It basically creates a data packet, okay, with both variables set as 1 and 1, and I'm going to put it to each of the message queues. Okay, so I have three message queues: red message queue, green message queue, and blue message queue, and I'm going to send it to each of them one after another. and each time I send a message queue to one of the LED messages, I'm going to wait for 2 seconds. Okay, and then first the red message for 2 seconds, green message wait for 2 seconds, and blue message wait for 2 seconds. And then in the last step, I'm going to send to all three immediately, one after another, and then wait for 2 seconds. Okay, so how are the three threads, the LED red thread, green thread, and blue thread modified to handle this? Okay, so basically what we are doing here is, at the start of each of these threads in the loop, we are waiting for a message to be received. Okay, so only if the message comes through, I will come out of the block state. If not, I'm forever waiting, okay, for some message to come in my queue. Okay, once the message comes in, okay, what am I going to do? I'm going to decode the message to confirm the command packet and data packet information. Okay, that is what I'm going to do. Okay, which is what I do for all the three threads. And if they are valid, okay, or if they have some expected combination, I will control the LED in a particular way. Okay, so that is what I'm doing, okay, for all the three threads. So what would be the expected behavior? Okay, so if I come back here, the very first time that I send out this message, I will be unblocking the red thread. So the red thread will come out of its block state, check that it is 1 and 1, and it will blink the red LED. So 1 second on, 1 second off, so the 2 second delay finish. Okay, once the 2 second delay finish, I'll come here, the green, and then I'll come here for the blue. So I'll see the red blink on and off, green blink on and off, and the blue blink on and off. In the last step, what will happen is all three threads will wake up concurrently, okay, one after another, and all three will go through the blinking at the same time. Okay, so what you will see is it will be red, green, and blue, and then white. Okay, when all three are lighted up together. Okay, so that is basically the observation you would observe, okay, or you would see in the lab as well. Now, definitely you may think that I can achieve the same thing with thread flags and event flags. Okay, so why message queues? Okay, so the main reason why message queues are so important is because of the ability to send data while synchronizing. Okay, in thread flags and event flags and semaphores, you can synchronize, but you're not transferring any data at the same time. Okay, but in message queues, you can send data and synchronize concurrently. So that is a very powerful feature of message queues. Okay, and though in this mini project you may not see much benefit because it may just be a 1 byte data, okay, but in reality you must imagine that I can send as much data as I need, okay, uh, through the message queue, okay, while synchronizing between multiple threads. So that is a huge advantage, okay, that we must acknowledge and take note of. Okay, so that basically wraps up the message queue portion. Now let's just quickly go through some important aspects. Though we have talked about it before, I think it is important that I reiterate this. Okay, data sharing is a very common thing, okay, in a multi-threaded program, but we have to make sure it is done safely. Okay, as we have seen before in the earlier slides, okay, there is always a possibility that things can uh, get messed up because of what we call a race condition. Okay, why? Because in a race condition, you have one thread possibly writing to some data, another thread reading from a data. Okay, and the relative timing of the read and write operations can never be predicted because of the preemptive nature of the OS. Okay, so any point of time you can be preempted, okay, and there can be interrupts, okay, all sharing the same data. Okay, so that is a very very important thing that we need to take note of. So what is important is we must look at what is the critical section of the code, okay, where there is access to shared data, and we need to put in some mechanisms in place to prevent a race condition from corrupting the data. Okay, and of course we have to understand that ARM is a load store architecture. Though we did not go into assembly language programming in this module, you have to understand that ARM is a load store architecture, which means that I cannot directly operate on anything in memory. I need to first, okay, load that data, okay, into memory, from memory into my registers, modify or do whatever operation I need, then finally store it back. Okay, So that is a very important thing. So even in C language, okay, if I write that A equals to A plus 1, a single line in C, but it is still multiple lines in assembly, okay, because I need to take the data from A, put into my register, increment, and then write back. Okay, so it is still multiple lines of code. So always remember, a single line in C does not translate to a single line in assembly. You still have to factor in at the assembly language level to see whether it is a critical section, or it is a code that can be preempted, okay, at the assembly level. Okay, and what we basically have to look at is whether you have single writers or multiple writers. If I have a buffer, okay, or some shared data where I have only one task writing to it and multiple tasks may be reading from it, okay, what you want is, you do not want a situation where both the reader and writer are trying to access the same data. So you do not want a reader and a writer to access the same data at the same time. Okay, so what you can do is you can put in some buffering. Okay, that is something that you can do at a programmer's level, or you can do things like message queues, where the writer writes to one message queue, the reader reads, okay, from the other end of the message queue or something. Okay, so some mechanism you can think of to implement that can avoid a race condition. In the case of multiple writers, where multiple people are now writing or multiple people are reading, okay, what you can do is what we have seen before, which is to use a mutex. Okay, so by using mutex, you are able to ensure that you are sort of locking the access, and then once the access is complete, you are unlocking it. Okay, so that is very, very important. In the event where you are unable to use a mutex, you can consider to options where you disable interrupts or you disable preemption. Okay, so for that brief period of time, you disable interrupts and or preemption to prevent a race condition from happening. Okay, and of course, another important thing you can do is you also want to make your tasks re-entrant. Re-entrant functions are basically functions where if multiple tasks are using the same function, we should ensure that the data that is used within the function does not get corrupted in any way. Okay, so for example, if I have a function called increment a, okay, and inside this function, or this function is called by task 3, okay, and it's also called by task 4. So this is a common function that is called by multiple tasks. Okay, so what I need to do is I need to make sure that whatever data that is used by this function is specific to that instance of that task that calls this function, and this is fine, okay, because automatically when you have automatic or dynamic allocation of memory, then it is fine. Okay, so what is important is you should not have any form of static variables or static objects within the function. Okay, why? Because when you have static variables within a function, what happens is that it creates a single instance that would be shared between multiple tasks. Okay, so that is one possible cause for data corruption. Okay, so it is important that if I have a function and I want to make it re-entrant, I do not have any form of static objects within the function. Okay, so that brings us to the end of this lecture slides. Okay, so like I mentioned, thread flags, event flags, and mailboxes or message queues are very, very good ways of synchronizing tasks as well as sharing data. Okay, and with this, okay, and and with the lab 9, you are basically ready, okay, to finalize the architecture for the mini project. Okay, so we have learned about threads, okay, mutex, semaphore, thread flags, event flags, and message queues. Okay, and all of this are very, very important and useful OS functionalities. Okay, and with all of this knowledge and information, you can decide and finalize the architecture you're going to use for the mini project. Okay, so good luck. Okay, and I will see you all soon. Thank you.